Hi everyone, we are continuing the third algebra workshop with the speech of the Deniz Yılmaz from Vefa High School. You can write your question in the conversation or ask them directly. It's your turn, Deniz.
Hi, my name is Deniz Cemal Yılmazsoy. I am currently in the Vefa High School at 10th grade. I'm studying at the IB program and this is my first speech, so I'm actually really excited to be here. I'll share my screen and slowly begin my speech. Perhaps you've heard of Évariste Galois. You know, the French mathematician who died tragically in 1833 in a duel. Well, today, we will be talking a bird's eye view of his most well-known contribution to mathematics, the appropriately named Galois theory. This theory might seem really dull. However, it can be used to solve and explain some important problems. Namely, some polynomials are not solvable by radicals. And the second one is that you cannot trisect an angle using a compass and straight edge. The first problem is that, given some polynomial fx, for example, let fx be ax squared plus bx plus c, such that a, b, and c are rational numbers. Our question here is that, is it possible to express the roots of fx using only rational numbers? Addition, subtraction, multiplication, division, and taking the nth root of a number, such that n is an integer. For example, given this fx, we can express the roots x1 and 2 as minus b plus minus the root of b squared minus 4ac over 2a. With the use of Galois theory, we can prove that for some polynomials that are quintics, namely, it contains an element x to the 5. It is not possible to express the roots in multiplication, subtraction, and division. And the second problem is that, given an arbitrary angle, such as 60 degrees, by using a straight edge, it's a ruler with no indication. There's only one, and there are no other indications of numbers, so you cannot use it to measure length. And a compass, we cannot trisect it in such a way that it is 20 degrees on each side. After having some motivation to study Galois theory, we may now start developing it. We will start by answering an seemingly easy question. What is the square root of 2? It's an easy question. For example, the square root of 2 is root 2 and minus root 2. Their numeric values are approximately 1.41 and minus 1.41, I'm sorry. However, we don't care about their numeric values. The thing we are after is that showing that they are algebraically not different. But what is algebraic difference? We can observe this by looking at some pretty basic examples. For example, the most important use of square root of 2 is that squaring square root of 2 equals 2. We can also notice that squaring minus square root of 2 is equals to 2. Also, we can observe more complex examples, such as the square of square root of 2 plus root 2 plus 1 is equal to 3 plus root 2. When we swap root 2 with minus root 2, we can see that the equation still holds. In general, given any algebraic equation with rational coefficients, any equation will still hold when square root of 2 is replaced by minus root 2. We will give one last example to this, such as 1 over root 2 plus root 2 over 2 equals root 2. When root 2 is swapped with minus root 2, we can see that the equation still holds. When we return to our original problem of what is the square root of 2, we still say that there are two such numbers, root 2 and minus root 2. However, we know now that they are not like any other two random numbers. They are like a copy of the same thing, namely, root 2 and minus root 2 are conjugates. Wait, conjugates over Q, where Q is the set of rational numbers. This means that swapping root 2 and minus root 2 will hold any algebraic equation where the coefficients are rational numbers. This is related to the fundamental question that Galois theory asks. Given some arbitrary numbers, that are conjugate over Q, how many ways are there to swap them that hold algebraic relations? For example, we can observe this equation. 1 over 3 plus 2 times minus root 2 is equal to 1 plus root 2 squared. If we swap root 2 and minus root 2, will the equation still hold? The answer is yes. It is also true in any algebraic equation with rational coefficients, but we can observe more than 2 conjugates. That means that we can swap conjugate numbers that have more than 2 conjugates. For example, we can observe the roots of unity. We will observe the 5th roots of unity. We will call the roots of unity alpha squared, alpha cubed, and alpha to the 4th. We can notice that alpha's conjugates are alpha squared, alpha cubed, and alpha to the 4th. Let's assume that an algebraic equation with rational coefficients holds for these conjugates, like C1 alpha is equal to C2 alpha squared plus C3 alpha cubed plus C4 alpha to the 4th plus C5. Our question here is that, is it true that equations will hold true no matter how we permute these alphas? For example, if I permute alpha with alpha squared, will the equation hold? The answer is actually no. That means that in some cases, the equations will not hold if we swap the roots. Likewise, if we swap alpha cubed and alpha to the 4th, the equation will still not hold. Actually, there are 4 ways to swap these roots that preserve algebraic relations. Alpha squared. The first one is not moving any of the roots. The second one is alpha squared, alpha cubed. The second one is that alpha goes to alpha 2, alpha squared goes to alpha to the 4th, alpha to the 4th goes to alpha cubed, and alpha cubed goes to alpha. We obtain a weird zigzag in this case. The other one is that alpha goes to alpha cubed goes to alpha to the 4th, alpha to the 4th goes to alpha squared, and alpha squared goes to alpha. The last one is that we swap alpha squared with alpha cubed, and alpha cubed goes to alpha squared, and then alpha goes to alpha to the 4th, and alpha to the 4th goes to alpha. This means that swapping conjugates of alpha in the ways given above will hold the equation true. But why do we swapping these conjugates? When we look at the way some numbers swap places, we can learn some things about the field that they are in. This is actually the basic content of the fundamental theorem of Galois. The examples we have observed were to grasp the concept. Now, we will try to generalize things by working with more flexible things. For example, from now on, we will switch from numbers to things called fields. And from talking to permutations, we will talk about automorphisms. But what are fields? We will give a basic definition now. Formally, a field is a set F together with two binary operations of F called addition and multiplication. A binary operation on F is a mapping FF to F. This means that we get two elements from F and send it to an element to F. It is a correspondence that associates with each ordered pair of elements of F a uniquely determined element of F. The result of the addition of A and B is called the sum of A and B and is denoted by A plus B. Similarly, the result of the multiplication of A and B are called the product of A and B, and they are denoted as A times B. These operations are required to satisfy the following properties, referred to as field axioms. First, A plus B plus C will be equal to A plus B plus C. This gives us the opportunity to add any element we want in any order. And also this will hold for multiplication, such that A times B times C is equal to A times B times C. Also, there is commutativity, which is A plus B will be equal to B plus A, and A times B will be equal to B times A. For every A in F, there will also be an inverse element of A, denoted as A minus A or A over minus 1. These elements will be used as the inverses, which means that adding A to minus A will give 0, and multiplying A with A to the minus 1 will give us 1. But what are 0 and this case, which is the fourth element of requirements of a field? Every F has a 0 and 1, such that A plus 0 is equal to A, and A times 1 is equal to A. We have one last requirement for a field, which is A times B plus C will be equal to AB plus AC. For example, we have the set of rational numbers Q. This forms a field, because if we add two rational numbers, it will be a rational number. Every rational number has an inverse, and we have 0 and 1s in rational numbers. However, in our above examples, we observed root 2. How will we observe root 2 in a field if the rational numbers does not contain root 2? We will do this by extending the rational numbers such that root 2 is contained in this field. This field is actually denoted by Q root 2. And Q root 2 is defined as every element a plus root 2b such that a and b are irrational numbers. I recommend you that you prove this by yourself to see that it follows the requirements of fields. Now that we have given the definition of fields, we will go to automorphisms. At this point, you may be wondering why I was talking about symmetries of roots at the beginning. For example, we swapped root 2 with minus root 2. But why did we do this? Here's where the idea of a field automorphism comes in. Let's use q root 2 as an example. If we define a function f from q root 2 to q root 2 by taking f of a plus b root 2 is equal to a minus b root 2, we find that f is what is called a field automorphism. Now, we will give the formal definition of an automorphism. A field automorphism f has to be invertible and is a function such that f of x plus y is equal to f of x plus f of y, and f of a times x is equal to f of a times f of x. The idea of a field automorphism is that it is just a way of relabeling the elements of the field without changing the structure at all. In other words, we can replace the symbol root 2 with minus root 2, do all our calculations, then change the symbol root 2, minus root 2 to root 2 again, and we get the right answer. Field automorphisms are the right way of expressing this idea because the condition that f of x plus y is equal to f of x plus f of y is equal, preserve multiplication, addition, and so on. More specifically, if we have a field extension, also a field extension is defined by taking a field, for example, Q, and adding a number such that it is still a field. For example, Q root 2 is a field extension of Q. We have a field extension K of a field F, then an F automorphism namely an automorphism fixing F leaves all the elements of F unchanged and only labels the new elements to the form K. It turns out that for Q root 2, the function F I defined above is the only Q automorphism other than real gx equals x. We will now use these in an example. Let's have a polynomial px such that it is x to the fourth plus 1 is equal to 0. The roots of the polynomials are alpha, alpha to the third, alpha to the fifth, and alpha to the seventh, where alpha is e to pi I over 4, which is equal to 1 over 2 times root 2 plus I times root 2. There are 4 possible automorphisms of these roots in this case. The first one is the trivial one. We name this identity. It is defined such that alpha goes to alpha. There are 3 more possible cases such that, for example, let us name this sigma, and let alpha go to alpha to the third in sigma. And this tau such that alpha goes to alpha to the fifth, and we might have the that is defined as alpha goes to alpha to the seventh. Now we will draw all of the automorphisms. For example, the identity automorphism is drawn like this: alpha, alpha to the third, alpha to the fifth, alpha to the seventh. None of them moves because alpha goes to alpha, which means that alpha to the third naturally go to itself, alpha to the fifth will naturally go to itself, alpha to the seventh will go to itself. Now we shall observe sigma. This means that sigma of alpha is equal to alpha cubed. Let this be alpha, alpha to the third, alpha to the fifth, and alpha to the seventh. Alpha goes to alpha to the third. Let us observe where alpha cubed goes to. Since alpha cubed is equal to alpha times alpha, this will be equal to sigma of alpha times sigma of alpha, sigma of alpha. Since these are equal to alpha cubed, this means that alpha cubed will go to alpha to the ninth. But we can see that there is no alpha to the ninth. We solve this problem by using a property of alpha such that alpha to the eighth is equal to 1. Since alpha to the ninth is equal to alpha times alpha to the eighth, alpha to the ninth will be equal to alpha. This means that alpha to the 3 goes to alpha. Now we can observe alpha to the fifth. Since this is equal to sigma to the alpha over 5, alpha to the fifth will go to alpha to the 25th power, which is equal to, I did a mistake, sigma alpha to the fifth will go to alpha to the 15th, and this is equal to alpha over 8 times alpha to the 7th. This means that alpha to the 5th goes to alpha to the 7th. And if we calculate alpha to the 7th, it will go to alpha to the 5. We can do this for every automorphism here, but I recommend you that you do these as an example so you can grasp the concept better. Now, we will take a slight detour to introduce ourselves to group. A group G, together with an operation dot, for example, combines any of the two elements of a group, A and and B, and it takes it to an element of G. Let us denote it by C. We have some conditions for a set to be a group, such that for all A, B, and C in G, A dot B dot C is equal to A dot B dot C. This means that we can take any order of operation we want. The second requirement is that there exists an element C, no, not C, E in G, such that for an element A in G, A times E is equal to E times A, that is equal to A. This is like the zero of rational addition. There exists one last requirement, such that there exists an element B, such that A times B will equal to A, and B times A will be equal to E. We call B the inverse of A, and this forms a group that is closed. After giving the basic definition of a group, we can return to the polynomial x to the fourth plus 1 equals 0. Now we will see that the automorphisms of this group, of this polynomial, will form a group. We had the identity elements such that alpha goes to alpha. We had sigma that made alpha go to alpha cubed. We have tau such that alpha goes to alpha fifth. And we had lambda such that alpha went to alpha seventh. We can notice that if we apply sigma to alpha, and then we apply sigma to sigma alpha once again, this will be equal to alpha, which means that applying sigma 2 times is equal to the identity element. And this means that alpha, no, not alpha, sigma is the inverse of itself. We can do this for tau, and we can notice that applying tau 2 times is equal to alpha once again. This means that tau is the inverse of itself. And if we apply lambda to itself, we can notice that this is also equal to alpha. That means that the automorphisms of this polynomial form, which we will call the Galois group of this polynomial. And we denote the Galois group of a polynomial as gal px. And this will be equal to identity, sigma, tau, and lambda. Each element has its own inverse, and it is a closed set. And this is the literal definition of a group. So the automorphisms of a polynomial form a group. After looking at these examples, we can start seeing a relation between the fields and the automorphisms. For example, let us take x to the fourth plus 1 is equal to 0 once again. At first, we looked at the automorphisms of x to the fourth plus 1 is equal to 0. Then we focused our attention to automorphisms fixing Q. And now we will focus our attention to automorphisms fixing the field extension of this polynomial. For example, let me draw a sketch of this field extension tower. Qi, Q root 2. And we have Q here. For example, we first looked at the automorphisms that fix Q, which are the identity automorphisms, sigma, tau, and lambda. And we want to look at automorphisms that fix Q root 2, for example, or Qi. Since that we are adding more requirements to the morphisms, that means that our groups will get smaller and smaller each time. For example, the automorphisms that fix Q root 2 are the identity and the lambda automorphisms. The automorphisms that fix Qi are the identity and sigma. And lastly, the automorphisms that fix Q root 2 and I is only the identity automorphism. This means that every subfield here, Q, Q root 2, Qi, Q root 2, and I, corresponds to a subgroup on the right. This means that every field gets a group that is unique to it. We can notice that there is a one-to-one correspondence between the fields and the groups we have constructed, which makes us develop the fundamental theorem of Galois theory. Let us have a field K that is obtained by extending Q, and let there be a field L in between. Let K satisfy the conditions of if alpha is in K, all of the conjugates of alpha have to be in K. And the L field is just an intermediary. For example, if K is Q root 2 and I, L can be Q root 2, and we have Q at the bottom. And we can notice that each field gets its own group of automorphisms. For example, Q is identity, sigma, tau, and lambda. Q root 2 has the group of automorphisms, identity, and lambda. And Q root 2i has the trivial automorphism, identity. We can denote this one-to-one correspondence like this. Let us denote the automorphism group as auth. If we have a field K and the subfield L, the subgroup of auth Q will be corresponded to subfields of K that contains Q. Now we will observe the one-to-one correspondence once and for all. If we have a field extension, let us denote it by Q alpha, the subgroup corresponding to it is the automorphism group of K, fixing Q alpha. The best way is to summarize this theorem is by saying the structure of a field is equal to its symmetries. Even knowing about this really makes me excited, and I wanted to give a speech about it just to make you have a general concept of Galois theory, because it is such an awesome theorem. I have nothing more to say. I have stated the theorem. I know I made some mistakes, but I tried my best. Thank you for listening.
Hatıra fotoğrafı alalım o zaman. İsteyenler kamerayı açabilirse çok güzel olur. Hatıra fotoğrafı için. Yok mu ya daha açan? Açanları yok galiba. O zaman alıyorum. Açan varmış. Bekleyelim biraz daha. Alıyorum. 3, 2, 1. Tamamdır. Şimdi bir aramız var. Sonrasında devam edeceğiz bir aradan sonra.